Hey everyone, I'm Xudong. Now let's dive into Chapter 2 of the Exploring the moyuefeng duo series, RT Thread on moyuefeng duo. This chapter is divided into 3 sections. First, we will introduce RT Thread. Next, we will explore running RT Thread on the moyuefeng duo. Finally, we will demonstrate how to control a LED using RT Thread. Let's start with an overview of RT Thread. Born in 2006, RT Thread is an open-source, neutral, and community-driven real-time operating system designed for the Internet of Things. Developed and maintained entirely by a Chinese team, RT Thread boasts full intellectual property rights. Over its 18-year history, it has evolved into a powerful, future-rich IoT operating system, especially with the rise of the Internet. The name RT Thread stands for Real-Time Thread, emphasizing its role as an embedded real-time multitasking OS. While it supports multitasking, allowing multiple tasks to run concurrently on a single processor, it doesn't mean that the processor executes all tasks simultaneously. Instead, the core switches rapidly between tasks using a task scheduler, creating the illusion of simultaneous execution. In RT Thread, tasks are implemented as threads. The thread scheduler manages these threads. RT Thread is primarily written in C, making it easy to understand and portable. It applies object-oriented design principles to real-time system development, resulting in elegant code and clear architecture. The system is modular and highly customizable. For resource-constrained microcontrollers, you can create a ultra-compact nano version using convenient tools. On the other hand, for resource-rich IoT devices, RT Thread supports online package management and intuitive modular customization, allowing seamless integration of rich software packages, including Android-like graphical interfaces, touching-based interactions, and complex features like smart voice interactions. Compared to Linux, RT Thread has a smaller footprint, lower cost, and a reduced power consumption. It excels in real-time performance and is well suited for resource-constrained environments. RT Thread is fully open source, following the Apache License 2.0. Users can freely use it in commercial products without rivaling proprietary code, eliminating potential business risks. Now, let's explore the key features of RT Thread. First, low resource usage. The minimal kernel requires only 1.2 KB of RAM and 3 KB of flash. 2. Rich components. RT Thread's ecosystem includes a thriving collection of software packages. 3. Elegance and simplicity. The code style is elegant and easy to read and master. 4. Scalability. The architecture is modular, loose-coupled, and easily extensible. 5. High performance. RT Thread supports demanding applications. 6. Wide chip support. It runs on various platforms, including ARM, MIPS, and RISC-V. Next, let's take a look at the architecture of RT Thread. At the lowest level, RT Thread supports different CPU architectures. Moving up, we have 3 main layers. First, kernel layer. Kernel layer is the core of RT Thread. It includes implementations of kernel objects such as threads, scheduling, semaphores, mailboxes, message queues, memory management, and timers. Adjacent to the kernel is the libcpu/BSP layer, which contains chip-specific files and board support packages closely tied to hardware comprising peripheral drivers and CPU porting. 2. Component and service layer. Above the kernel, we find components and services. Components are higher-level software built on RT-Threads kernel. Examples include the virtual file system, FinSH command line interface, network framework, and the device framework. The modular design ensures high cohesion within components and loose coupling between them. 3. Software packages. Further up, we have software packages. These run on RT-Threads IoT OS platform and cater of various application domains. Software packages consist of descriptive information, source code, or library files. RT-Thread provides an open package platform where both official and community-contributed packages reside. Currently, RT-Thread supports over 450 software packages. Now, let's move on to running RT-Thread on the moyuefeng door. The official support for RT-Thread on the door is already merged and located in the CVITech directory under the BSP folder. The current status is that the big core is supported, running in the standard RT-Thread version. The latest version now supports both CV118 series and the CV181 series, corresponding to the 256 MB and 64 MB versions of the door. For our demonstration, we will use the basic door 64 MB version. This time, we are using an older commit version, specifically AC2F7F05. The big core has the MMU enabled and runs in RT Smart mode, while the small core lacks MMU and operates in RT Thread standard mode. The UART configuration is as follows: UART0 for the big core and UART1 for the small core. Now let's take a closer look at the specifics of both cores. The current page focuses on the application version of the CV1800B chip. It includes an overview of the CV1800 series chips and the supported peripherals. Moving forward, we will discuss how to compare RT-Thread and run it on the moyuefeng door. First, navigate to the RT-Thread directory. Since we are using an older version, execute the git checkout b command to create a new branch named moyuefeng and specify the exact commit version. Next, head to the BSP directory, which contains board support packages and hardware-related files at the kernel level. Inside the CVITech path, you will find two folders, CV1800B and C906 Little. Let's start by exploring the content related to the big core. Before processing, ensure that you downloaded the necessary toolchains. In the Downloads directory, you will find the RISC-V Linux MusiLab for x86 64 PC Linux GUN toolchain and the Xuantie 800 GCC toolchain. These are essential for comparing both cores. After downloading the toolchains, the first step is to install dependencies. You've already compiled this step, including installing the device tree compiler package. Now let's modify the configuration using sconce menu config. Since our version only supports the dual 64M, you can exit the configuration menu without making changes. RT-Thread will generate a suitable configuration file, Additionally, update the package dependencies using pkjs update. Finally, compile using sconce. The optional parameter G10 specifies the number of cores to use during compilation, but you can omit it and use sconce directly. I forgot to modify the rtconfig.py file. You will notice a specified path there. Since we saw the path is within the downloads directory, adjust it accordingly before processing with the compilation. The compilation process is quite fast, and once compiled, it will package the output. The mksd image.sh script will automatically create the boot.sd file, which serves as the DOS kernel during startup. You will find this file in the parent directory. Now, let's switch our focus to the small core. Similarly, refer to the README for compilation requirements. First, download the Xuantie 800 GCC toolchain. Pay attention to the version numbers. The downloaded Xuantie 800 GCC version is v2.8.1, while the rtconfig specifies v2.8.0. Make sure to update the version to the 2.8.1. The toolchain has already been added to the environment variables. Now, let's continue by executing moyuefeng to modify the configuration. No further modifications are needed. Next, import the configuration file and run packages update to ensure the software package dependencies are up to date. Finally, proceed with the compilation. The compilation process is remarkably fast. Once compiled, the combine fip.sh script will package the output, resulting in the fip.bin. This file contains the content for the small core. Although the slide mentions generating fip.sd, in reality it generates fip.bin, which corresponds to the small core's runtime content. At this point, the RT thread system for running on the moyuefeng duo is fully compiled. The next step involves placing boot.sd and fip.bin onto the SD card. As mentioned in the slides, we need to partition the SD card into two partitions. The first partition for storing RT threads binary files, and the second partition for data storage. Both partitions should be formatted as FAT32. First, use the fdisk-l command to view the storage devices on your computer. When a SD card is inserted, it is typically labeled as /dev/SDA and has a size of 59.48 GB. Proceed with partitioning using the fdisk utility. Create two partitions. The first partition with a default starting position and a size of 4 GB. Remove any existing formatting. Then create the second partition without any specific size restrictions. After saving the changes, verify the partition layout using fdisk-l. Although SDA1 and SDA2 are now properly partitioned, their formats are incorrect. We need to adjust the format to FAT32 using the fdisk utility. To modify the file system type, use the T command. Press M for help, and you will see that T is used for changing the partition type. Apply this to the first partition. To specify the correct format, press L to view the available options. Choose 0C for FAT32 and enter C. Repeat the process for the second partition, using the default value of 2 and selecting C. Finally, save the changes. Verify the partition layout again using fdisk L to ensure it meets the requirements. The SD card partitions are now ready. Next, format each partition. Use makefiles.fat f32 to format the first partition and proceed similarly for the second partition. A quick reminder, during the first step, there's no need to create partitions first and then modify their formats. You can directly modify the format using the T command immediately after creating the partitions. I'll quit, then revoke it. The main purpose is to demonstrate each step of the operation and what kind of changes it will make. Now that we've compiled the initial setup, creating and formatting the two partitions, it's time for the second step. Copy the fip.bin and boot.sd files from the root directory to the first partition of the SD card. Mount the first partition of the SD card to /mnt and use sudo cp to copy fip.bin and boot.sd to the /mnt directory. After copying, unmount the SD card and insert it back into the moyuefeng door. Next, observe the moyuefeng door's status. You will notice two serial ports. The one closer to the SD card is serial port 0, and the upper one is serial port 1. Connect both serial ports to your computer using USB to TTL modules. You will see that the small course content rapidly prints out is running the RT Thread Standard Edition and displaying Hello RISC-V. As for the big core, its output reads Hello RT Smart. Both the large and small core outputs are now complete. Let's verify the small core's content. Confirm that the small core indeed outputs Hello RISC-V. The main code snippet the small core simply prints the message. Similarly, check the big core's code by opening main.c in the application directory. It should output Hello RT Smart, which aligns with our expectations. So far, we've successfully launched RT Thread on the moyuefeng door. The remaining steps involve running tasks on the big core, such as controlling the LED. Next, let's explore the logic behind lighting up the LED on the moyuefeng door. First, we need to examine the circuit schematic of the moyuefeng door to locate the LED spin. For the blue LED, we can find that it is connected to pin GPIOC24. This means that manipulating GPIOC24 will affect the LED's state. We've now confirmed that we need to control the LED using pin number C24. But how do we control the LED? There's a circuit in front of the LED responsible for controlling its illumination. Let's continue to the next slide for the explanation. The principle of LED light up is depicted here. The component we previously discussed closely resembles a NMOS transistor, a type of MOSFET. Its operation is based on whether the voltage exceeds or falls below a threshold. In NMOS, when the gate voltage exceeds the source threshold, the entire circuit becomes conductive, causing the LED to emit light. However, in a PMOS, it is opposite. The circuit becomes conductive when the gate voltage is below the source threshold, resulting in LED illumination. In the Milky Way door, we indeed have a NMOS. To make the LED emit light, we need to apply a high voltage to exceed the source threshold. As you've observed, the LED is connected to pin C24. By setting GPIOC24 to a high voltage, the LED circuit becomes conductive, causing the LED to light up. With this conclusion, let's explore how we can control the pin in RT thread. In RT thread, we found a command called pin. Let's demonstrate it. There are a total of 5 options, excluding the help option. The first option is pin num, which retrieves the specific numeric value corresponding to a GPIO pin. Since we know that the LED is connected to C24, let's test pin number C24. It returns the value 536 for C24. Based on our earlier conclusion, applying a high voltage to C24 indeed makes the LED emit light. However, our first step is to set the model of pin C24 to output so that it can deliver voltage. First, execute pin mode C24 output to set C24 as an output pin. Next, use pin write C24 high to modify the voltage on C24. When set to high, you will notice the LED lights up. To turn it off, use pin write C24 low. We've been directly manipulating C24, but does the value 536 returned by pin num C24 also work? Let's try it out. As expected, writing high or low to pin 536 also controls the LED illuminating or extinguishing it. This confirms that 536 corresponds to pin C24. Thus we can control the LED using the command line. Is there a way to control the LED using a program? Yes, there is. While exploring the RT thread API documentation, I found a structure related to pin control, RT pin write and RT pin mode. These functions can achieve all the operations we previously accomplished via the command line. However, they belong to the RT device library, so you will need to import that library when using them. Let's dive into the code. I've already prepared an example. First, take a look at LED.h. It defines 3 methods corresponding to LED initialization, turning the LED on and turning it off. Additionally, it specifies the LED pin number. In the RT pin context, directly using C24 doesn't work, so we need to use the numeric pin value obtained earlier via pin num. Now let's examine the logic in LED.C. The first step initializes the LED using RT pin mode, which sets pin's working mode. There are two parameters, the pin number and the mode. For LED control, we need the output mode, so we set it to pin mode output. This initializes the LED. To make the LED emit light, we use RT pin right to set the pin voltage. By default, the value is 0, and you can choose between pin low and pin high. Since we want the LED to light up, we set it to high voltage. To turn off the LED, we set the pin to low voltage. This covers the LED control logic. Finally, I made a modification to the kernel code. Since the LED responses happen very quickly in the program, we might miss them seeing the LED light up and then immediately turn off. To observe more clearly, I added a delay. First, the program outputs Hello RT Smart. Then, after initializing the LED, it waits for 5 seconds before turning the LED on. After another 5 seconds, it turns the LED off. Although the code appears to output before controlling the LED, the machine's computational speed is so fast that our perception doesn't distinguish the order. Essentially, they run simultaneously. After turning off the LED, it waits another 5 seconds before turning it back on. The entire program concludes. This program demonstrates LED control. You can copy it into the application folder within CV1800B. The application directory contains RT-thread program code. Use CP to copy the LED control code, recompile, and obtain a new boot.sd. Remove the SD card from the door. Mount it to /MNT. Copy boot.sd to /MNT. Unmount, power up the door, and observe the LED behavior. It lights up, turns off after 5 seconds. And then lights up again after another 5 seconds. That wraps up the entire process of porting RT thread to the moyuefeng door. Thank you all for watching. Feel free to experiment with LED control using RT thread. Feel free to share with me if you have better suggestions or ideas. Thank you all.